Good morning, everybody. In this lecture, we're going to study modeling of mechanical systems. This class, the objective is to simulate physical systems. So simulation first requires a model. We're going to study mechanical systems in this lecture and then electrical system in the next one. These two lectures are relatively simple. So we're going to try to do as many exercises as possible because this is the foundation for what you're going to see next. These are the only two lectures strictly devoted to mechanical and electrical systems. It's very important that you understand them because later we'll combine the mechanical and electrical systems and even try to make it the analogy between them. Okay, but the contents of this lecture are not hard at all. A lot easier than the last one. So regarding the last lecture, we discussed last Wednesday that we could potentially do more exercises. What I suggest we do today is to go over this lecture, do it one exercise or two, and then see if you feel the need for more exercises on modeling of mechanical systems, or if you'd like to go back to lecture 2 and do one more exercise on convolution integral. Okay, so let's do that. Let's go start with lecture 3, do a few exercises and see if you have time, and if you feel that this is simple enough, then you can move back to lecture 2 and do one more exercise on convolution integral. If we don't do that, that's fine. I posted the solution to all exercises that I had in lecture 2, and I think they are relatively self-explanatory. Okay. All right. So let's get started here. Modeling of mechanical systems. Next lecture, modeling of electrical systems. I know that most folks that are not in electrical engineering are a bit scared of electrical systems modeling, but really this is very simple. There is nothing complicated about it. So by the end of this lecture, you should be able to sketch a free body diagram of mechanical system, derive the equations of motion of mechanical system, and understand what different inputs mean to a mechanical system. So let's jump right into it. In order to model a mechanical system, we need some building blocks. We need some basic elements that will represent different components in the mechanical system. We're going to use what we call a lumped model, meaning that we have discrete elements that will model or a continuous system. These elements are a mass, a damper, and a spring. So we're going to make some idealizations for each of these components, and here is the first one. Is the mass or the quantity of matter in a body. A mass will create some inertia, that is a resistance to change in speed, a resistance to change in its state of motion. A rigid body is the assumption you're going to make here. All masses are rigid bodies. They do not change shape. They do not have any sort of stiffness or viscous friction. They are rigid bodies. They do not deform, and their masses are constant. So let's now derive the equations of motion for the two most simple systems, a mass subjected to a force and a that is subjected to a linear motion, and one that is subjected to a rotational motion that has certain inertia. Starting with the first one, here we have a force applied to a mass. This block is representing the mass, and this block has a displacement x. This is the displacement of that mass. How do we relate now the force applied to that mass? Well, we know that the sum of all forces acting on a body is equal to the mass times its acceleration. In terms of displacement, we could say that this is equal to the mass times the second derivative of its displacement. All right, the mass times the acceleration, or the second derivative of the displacement. In order to simplify the notation, we're going to use a new notation here. We're going to use the variables with dots on top of them. And every time we have one dot, that means the first derivative, two dots, second derivative, three dots, third derivative, and so on. So we can say that a dx dt is x dot, which represents here the speed of the mass. And the double derivative of x with respect to time, you're going to call that x double dot. That is the second derivative of x, that's the acceleration of the mass. So our equation here could simply be rewritten as the sum of forces equals to mass times the second derivative of x, mx double dot. Okay. If we now move to a rotational system, instead of linear displacement x, we have an angular displacement. You're going to call that theta. Instead of a force, we have torque. And instead of mass, we now need to account for the shape of that object, how it rotates around a given axis. And as such, we need to use its second moment of inertia that we call here J. So this is the moment of inertia. This is the torque. And theta is the angular position. So now we can do the same sum of all torques equals to the moment of inertia times the acceleration of that disk. Let's call that the acceleration alpha, which in relation to the displacement can be written as J times theta double dot. J times theta double dot, which is the same as J d theta dt squared. Right? The second derivative of the angular position is the angular acceleration. So sum of torques equals to J theta double dot. Okay, or J is the second moment of inertia of that disk with respect to that specific axis of rotation. Any questions here? No? All right. So that is the first element. Anything that we want to model will have a mass. And if now for a given system, we have some level of deformation or the system has some stiffness, we have to add that element to the model as well. And that's where we're going to use a spring. A spring is an element, a mechanical element designed to store energy. The idealization that we're going to make here is that a spring has no mass and has no damping, is a purely elastic element. Okay, so if we have, for example, we want to model something that deforms and that thing has a mass, we need to use two elements. One is a spring connected to that mass. So a spring has a stiffness constant K here, which gives the relation between the force and the displacement. The displacement of one end of the spring is x1. The displacement of the other end of the spring is x2. And the total displacement of the spring is x2 minus x1. That is the relative displacement of the spring. We are measuring this with respect to a fixed reference frame, which means that if x2 and x1 move together by the same amount, the spring is not compressed nor stretched. It's just translated. But so long as one end of the spring moves more than the other, then the spring is either being compressed or stretched. And that amount of displacement is x1 minus x2. Now the force developed by the spring when it is in a state of compression or is being stretched is force is the function of time, is the stiffness constant K times the relative displacement of each end of the spring, x2 minus x1, or x1 minus x2. But in this case here, if we are assuming that we are stretching the spring on the left side, on the right side, we can say that x2 is greater than x1. It will move in a more in a state of transient. At the beginning, we can say that x2 will start to move faster than x1, even though that is not correct. We can picture that as x2 moving slightly faster than x1 in the beginning of motion. And then we can say that x1 is greater than x2 is greater than x1. You can write x2 minus x1. Okay. Of course, that is not correct, but it's just a way to find the signs and which one moves first, or in which way you can arrange the equation. But we could have put x1 minus x2. It would be correct as well. You just find a negative sign at the end. If one end of the spring is fixed, for example, x1 is attached to a fixed reference frame like that, and it doesn't move, then x1 is simply 0, and the force becomes K times x2. Okay, but both ends may be moving. So what is the unit for K? Well, F is in newtons. We need a unit for K. the displacement is in meters. So in order to balance the units here, we need newtons per meter. That's the unit for K. We can now move on to the equivalent in now a rotational system. Instead of a linear stiffness, we have a torsional stiffness. And instead of torque, we have force, we have torque. Instead of linear displacement, we have angular displacement, theta 1 and theta 2. So we can do the same now. Sum of all torques, or the torque produced by the spring tau of T, is the stiffness of the spring times the relative displacement, angular displacement in this case, theta 2 minus theta 1. What is the unit for K in this case? Well, torque is in Newton meters. Theta is in radians. So what do we need K to be? We need it to be Newton meter per radian. That's the unit of K. All right. Any questions? Nope. All right. The last element we need is a viscous, something to account for viscous friction. And we're going to introduce here the concept of viscous damper. The idea of having a viscous damper is to dissipate energy in a mechanical system. The idealization for this is that it has no stiffness and it has no mass. If you want mass and stiffness, we need to use the other two elements. So the damper will be represented by this symbol that we see here. Assuming the displacement of one side of the damper is x2, the other side is x1. It works similarly to a spring, but now instead of being the force being dependent on the displacement, it depends on the relative speed of each side of that damper. And the relation between the force and the speed is the viscous friction coefficient B. So the force developed by the damper in the case of the linear system is simply the coefficient of viscous friction times the relative speed of the damper on each side. How do we write the speed? Using the notation we just established. x2, if x2 is the position, then x2 dot is the speed. So x2 dot minus x1 dot. Okay, and what is the unit for that? Well, for B, force is in newtons. B we want to find. The speed is in meters per second. So obviously, to balance the equation, this value of B needs to be Newton second per meter. And then when you multiply everything out together, you get newtons. Okay, so one thing to, all right, let's move on to the rotational one, which is very similar. And then I'm going to add some considerations to this. So the torque developed in the rotational system is the coefficient of viscous friction times the relative speed of each side, but it's now angular, theta 1 minus theta 2. Now, the torque is in Newton meters. The value of the unit of B will determine. And angular speed is in radians per second, meaning that to balance the equation inside here, we need Newton meter radian, sorry, Newton meter second divided by radian. That's the unit for B. Okay. Now, we are talking here about viscous friction. Viscous friction is not the same as static friction. Or kinetic is more I wouldn't say this. Let's forget about this kinetic friction here because it might be confusing. It's not the same as static friction. Static friction is the amount of relates to the amount of force you have to apply to get an object moving, start moving. So you might have to apply a given force, and there is a threshold after which the system starts to move. That's not what is happening here. You're assuming here that there is a resistance to motion, a force generated that increases as with the speed of that object. You can think about putting your hand in a pool, water, and moving your hand slowly or moving your hand fast. The faster you move, the harder it gets for you to move your hand in the water. Right? So there is a relation between the speed of your hand in the water and the force you have to apply to get it going at that speed. and that relation is a viscous friction. Is the viscous friction between your hand and the water, given here by this constant p. Okay, so this would entail that we are dealing with a linear system. If we deal with a static friction, something like this, or something like have a certain force here, certain displacement to reach before the thing starts moving, this is not linear and we cannot account for that. So we need to limit our analysis to things that are linear, and the viscous damper, because the force is directly proportional to speed, is a linear system, and then we can use it. Okay? Any questions here?
One quick question, Professor. What does the dot mean on top of the theta, and the x?
So that's the notation we established in this slide here. The first, every dot means one derivative. Right? So x dot is the first derivative of x with respect to time. X double dot is the second derivative of x with respect to time. So if x is the position, then x dot is the speed, x double dot is the acceleration. If v is the speed, then v dot is the first derivative of the speed, which is acceleration as well.
Thank you, sir.
Okay. Any other questions? Okay. All right. So we have all the elements we need. Now we can start to put them together to create a system. But when we put them together, like in this example here, we now need to analyze which forces are acting on each mass and replace these elements with the force they create on that specific mass. So basically what I'm saying here is that the first step to derive the equations of motion is to create the free body diagram that you learned, I'm certain, in another class. But let's revise it briefly. So here we have two masses. Each mass is they are connected by a spring. One mass is connected to a wall. This mass is sliding on a surface, and we can assume that there is friction between the mass and the surface. There is viscous friction, and let me say that viscous friction has a coefficient B1, and the damper on the other side has a coefficient of viscous friction B2. The second mass is on top of those rollers, and this is just to indicate that there is no friction between the mass and the ground, so no friction here. So now let's create the free body diagram for each of these masses. For mass M1, we have to now replace the effect of all these elements by the forces they produce. So force F of t is still here, applying a force to that mass. If you now hold mass M2 and apply force M1, you see that the effect of the spring K on mass M1 is pushing against force F. If I hold mass M2 steady and I displace mass M1 in the direction of force F of t, there is a spring now between the fixed mass M2 and mass M1 that is moving towards it, and that spring is pushing against mass M1. So that spring can be replaced with a force. Let me call this force F of K, which is the force due to the spring. As mass M1 moves to the right because of force F of t, there is friction between the mass and the floor and the ground. And that friction coefficient B1 will also create a force that will always oppose motion. Therefore, it needs to go in the same direction as the spring. And this will create a force FB1 that opposes motion of that mass. Okay. We can do the same for mass M2. What is happening? Well, if we look at the system now, the spring, because mass M1 is moving to the right due to that force F of t, it will compress the spring, and the spring will push mass M1 to the right as well. So the spring will now apply a force F of K to the mass. You notice here that is the same force that was holding mass M1, but it's now in the opposite direction, meaning that when you connect these two blocks together, these forces will cancel out. It's the same magnitude, but in opposite directions. What else is happening here? Well, the other force acting here is the force due to that of viscous friction coefficient B2, and it's also opposing motion. And that is going to be F of B2. Okay, so these are all elements added acting on these masses. Then you can do the sum of forces equals to mass times acceleration or second derivative displacement and create equations of motion. But we'll do that in the next step. Let's just do one more free body diagram here. Let's do mass M1 first. So which forces are acting? How many forces are acting on mass M1? How many forces? How many forces are acting here?
Would there be 3 forces?
There will be 3 forces plus the one that is not indicated here was this viscous friction between the mass and the floor. You actually have 4. I didn't indicate here, but if we have friction, if not indicated, then 3. If we have friction there, then you have 4. So let's assume that we have friction. What is happening there? If we hold mass M1, we're just dealing with mass, hold mass M2, we're just dealing with mass M1. There is this x of t, which is a displacement being applied to that mass, the spring. If we are applying displacement to the spring, that displacement will push mass M1 to the right, meaning that that spring, let's call this K1, will create a force Fk1 pushing it to the right. The stiffness, the spring K2 here will hold the mass, will push against the mass, so we'll apply a force in the opposite direction, Fk2. If mass M1 is going to the right, and mass M2 is fixed, then you can also assume that there is a displacement, that there is a force from the viscous friction coefficient from B2, which is Fb2 going against it. And we also have the effect of the friction between mass M1 and the floor under it. That friction there creates a force against motion, Fb1.
I have a question.
Yeah.
So is the force from the damper going through the left side there into M1?
This force over here is Fb2, and this force is Fb1. It's not the damper. That force B1 is the friction coefficient between the mass M1 and the floor. And B2 is between the damper that connects two masses.
Okay.
Okay.
Thank you.
Yeah. All right. And now let's do M2. What is acting on M2? We have a force F of T. If the spring pushes M1 to the left, and now we need to do M2 to the right. So when you connect them together, they canceled out. And the force due to friction, due to the damper here, Fb2 is pushing against the mass as well. Right? So that when you connect everything, you notice that these are going to cancel out. Now, there is a potential for confusion here because we are representing friction in two different ways. The first one is between the ground and the mass, and we said that, well, this is a viscous friction coefficient, B, and also be using this symbol, but they represent exactly the same thing. Exactly the same thing. Right? And these are pretty much equivalent. We could write, for example, this, or we could say this instead. Now they are exactly the same. Any questions here?
Sir, could we not use, maybe it's a bit of a redundant question, but couldn't B1 can I just like on examples or in problems, can I just put B1 as just friction? or is that?
Can you use? Sorry, I didn't catch the last part. Can you use only what?
Is I'm a little confused. Is B1 isn't that friction? Why
Yes.
do we? Is it just does it act as viscous for a viscous damper?
Yes. It acts exactly like a viscous damper. As I said back here, we should not confuse a viscous damper, a viscous friction, with static friction. It's not a static friction.
So then what is it like? Is it more like kinetic friction?
It is more like kinetic friction. Yeah.
Okay, all right. Just want to clear that up. Thank you.
Yeah. So one example that might help you visualize it is, even though this wouldn't be linear, but if you try to move your hand in the water or try to walk in water, the faster you walk, the harder it gets. The harder it gets, the more energy you have to deliver. The higher the resistance of the water against you. Right? And it's the same here. The faster it moves, the more force is created from friction. Okay, so let's do one more free body diagram. Here we have a stack of two boxes and one force. This was from last year. We had a question on the midterm with this. It's two boxes stacked like that as a force applied to one of the masses. What are the forces? What is the free body diagram? Let's start with this one here. Let's start with mass M1. M1 actually, let's start with mass M2. What is happening in mass M2? What is there any force acting on mass M2? Is there any force acting on mass M2? We have two boxes stacked. We apply a force to the bottom one.
Would there be like a viscous damper friction or whatever you call it?
Exactly. There is viscous friction. You can easily visualize that if I have a paper here and I have an object on top of it. I put a mouse on top of it and I'm moving now this paper. Why is the mouse moving? Because there's friction between them. And if this moves to the right, friction is making the mouse move to the right as well. So there's a force here that is generated between these two masses and is making M2 moving in the direction of M1. Let's call that friction B1 that exists between these two boxes here. And that's the only force acting on that mass. What is acting on M1? Well, on M1, we have the force F of t. If there is friction between M1 and the floor, here we have a force FB1, FB2. And if mass M1 and mass M2 are subjected to this friction FB1 and FB1 acts on the right on mass M2, then it needs to act towards the left on mass M1. Okay, so that when you put them together, they cancel out. All right. The next one here is very similar. I'm gonna skip this one and just post the solution, the free body diagram later. It's exactly the same, just forces may change sign. Okay. Any questions?
Yeah. So for FB1 on M2,
Mm-hmm.
Wouldn't that be static friction? I'm just curious.
No.
Or why is it considered viscous instead of static?
Because you cannot model static friction.
Okay.
We cannot model static friction because it's not a linear. It's not linear. And in the example I gave here, this is more like static friction. But if I move fast, you see that the mouse moves on top here, right? And as it moves on top here, there is still friction between the two. And that friction depends on how fast these things are moving with respect to one another.
Okay, so M2 would be kind of sliding as M1 is moving.
Exactly. They slide. There must exist a relative displacement between them and relative speed for a force to exist. Right?
Okay.
So if we move mass M1 by 1 millimeter at a given speed, mass M2 may be moving slightly slower so that there is friction to keep it going. Right? It's not a static friction. There is static friction, but we cannot account for it. Okay, so let's do another example. One example here. We have this mass that is attached to a spring and a damper, and as I mentioned, we can represent this viscous friction that acts here between this mass and the fixed reference frame as being the same as friction that exists between a surface and the mass. So these two arrangements, these two figures are exactly the same. Okay, there is a spring connected to a reference frame. There is friction between the mass and the fixed reference frame. So either of these arrangements works. And they represent the exact same thing. So now let's create the free body diagram for this. If we are moving mass M1 to downwards, then friction and the stiffness will try to prevent the mass from moving, so they will be applying forces upwards. If we can say that this mass is moving downwards with a displacement x of t, now what is the magnitude of the forces each of these elements apply? Well, for the stiffness, for the spring, we have only one end of the spring moving. That is the displacement of the mass is the same displacement as the bottom side of the spring. So the magnitude of that force developed by the spring on the mass is k times x of t. And friction now depends on the speed of the mass, which is the same speed as the other one of the ends of that damper. The other one is fixed, it doesn't move. So this force is b times x dot of t. X dot is dx dt, which is the same as the speed of the mass. Okay. Now we can do the sum of all forces acting on the mass is equal to the mass itself times its acceleration with respect to the variable of interest x, which is a displacement, is x double dot. Now we are in a position where you can sum of all these forces, but before we do that, we need to establish a convention. Forces going in a specific direction will be positive, forces going in the other direction are negative. For simplicity here, because we know that the mass is accelerating downwards, because the force is going downwards, we can say that anything that points downwards that is contributing to the acceleration of that mass is positive. So here we have sum of all forces. What are these forces? We have force F of t that points downwards, that is positive. And you have two negative forces pointing upwards, minus k times x of t, minus b times x dot of t. And this is equal to mx double dot. And this is the equation of motion for that mass. If we had added gravity here, then this would add a component plus mg to be added to the equations. Right? But this was not specified, so we don't need to account for that. Okay, x displacement, x dot speed, x double dot acceleration. Any questions? Okay, so the only mistake, a common mistake I see students making here, which is a critical mistake, is to treat mass times acceleration as a force and put that on the left side of the equation, assuming that that's a force somehow. And then they mix up all the signs, right? That's the result of the sum of all forces. It's not a force in itself. It's a result. It equates to a force, but it's the result of all forces acting on the body. Okay, so this equation holds all the time. Let's do a rotational system instead now. So in this rotational system, we have a mechanical shaft that is connected to a torsion spring of stiffness K. The coefficient of viscous friction between the shaft and the bearing is B. If subjected to a torque T, determine the equation of motion. Okay, so we can represent this shaft as perhaps a disk, like that. And we have three forces acting on this disk. We have the torque that is being applied to create motion, that's capital T. And let's assume here if that goes clockwise, there is a torsion spring attached to the shaft, which means that the torsion spring, as soon as it is deformed, will create a force, torque, that opposes that displacement. So there is one force due to the spring. And as the torque creates acceleration or speed in the clockwise direction, the torque generated by friction between the bearing and the shaft will oppose motion and create another torque that opposes the acceleration, opposes the speed. What is the magnitude of the spring torque? Well, it's simply K times theta, where theta is the displacement of the spring. And what is friction is B times theta dot, which is the same as B times omega, if omega is the speed, angular speed of the shaft. So these are all the forces. We can now do sum of all torques equals to the moment of inertia of that shaft times its acceleration. If we consider theta the displacement, then you can write this as theta double dot. Because it's accelerating in the clockwise direction, anything that goes in the clockwise direction by convention, we can say that's positive here, which means that we have a positive T minus K theta because it's going in the counterclockwise direction, and minus B theta dot, B theta dot. So these are all the forces acting on it, equals to J theta double dot. Okay, you notice here, this is a second order differential equation, same variable theta, first derivative, second derivative, and this is the equation of motion for this system. In lecture 4, we'll solve these equations using the Laplace transform, and then we'll be able to determine the output of the system. For example, if you apply this torque, this will be the profile of displacement or speed or acceleration. Okay? Questions?
Just one quick question. Did you write B omega?
Yes, omega is just a common sign for a speed, angular speed, which is the same as theta dot.
Thank you.
But of course, we want the equation to only have one variable, so we write everything as a function of the same variable, in this case, theta. Okay. Any questions? Any other questions? No? All right. So when we define now the model, for now, we are unable to determine the output of the system because we need to solve the differential equations. We'll do that later using the Laplace transform. But for now, let's stick with modeling the systems. And maybe try to understand what it means to apply these inputs to these systems. So we have 4 common input signals that it could be a displacement, could be a speed, could be a force applied to each mass in the system. The impulse function, we treated that in the last lecture, is a large amount of energy that has been applied to the system at a given time and then removed. The step function is a signal that is applied at a given time and then held constant. A ramp function goes up over time, and a parabolic function is the same, but it goes up non-linearly. We have, here is a description of what they mean. I'll skip this because this is from the last lecture, just as a reminder here. But let's assume, for example, that we have this mass spring damper system, and we want to apply a step and an impulse to this mass. Let's start with the step response. So a step response, in this case, would be the step response to an input force. What does it mean to apply a step force? Well, by definition of the step function is a function that in this case would start at 0 and then held constant. So what does it mean? We are applying a force at time 0 to this mass, and then holding that force constant as time goes to infinity. What happens to the mass itself? Well, as soon as we apply that force, the mass will start moving. And it start moving. If we look at the displacement of that mass, the mass will start moving, and eventually, as it starts to move, the spring will oppose motion, so will friction, but eventually the amount of force developed in the spring will be exactly the same as the force we are applying, because you keep stretching the spring, the force keeps increasing, and eventually will balance out with the force we are applying. And that force is held constant, meaning that at some point we reach the maximum displacement and the system will settle. So if you look at the time response, or how the position evolves for a step input, we should see something that resembles, for certain values of k, m, and b, this. Of course, it could also be an exponential. We'll see that later, but we'll see something like that. What I wanted to observe here is that the system settles at a non-zero displacement. And once it settles, it stays at that displacement. All right. If you look at the impulse response would now be a bit different, because we are giving a large amount of energy to the system at time 0, like slapping the mass very fast. Slapping the mass, it will just oscillate and then settle back where it was at 0. So it will eventually settle at 0. So in 1, the impulse function, we slap the mass and oscillates and comes back to where it started. The impulse, we apply a force to the mass, and then you hold that force after the system reaches a steady state, after the system reaches equilibrium and stops moving. Okay, so one settles at 0, the other one doesn't. We can look at the speed response to a step and an impulse. It is the same idea, but notice the difference now. If you apply in the first case where you have a step being applied to the system, once the system settles, the speed is 0. So by applying a force in a step fashion like that, of course, the speed will first increase because the mass will start moving. And once it reaches equilibrium, once the force I'm applying is the same as the reaction force, it will stop moving. And hence, the speed here, this is the speed response, will settle at 0. Now look at the impulse response in terms of speed. We are slapping the mass at time 0 with an infinite amount of force. So you're creating at time 0 a non-zero speed, you see, because we are slapping the mass at time 0 with an infinite amount of energy. So the speed goes from 0 to a non-zero value immediately, and then eventually oscillates and settles at 0. Okay, so the previous slide is the speed, the position response in terms of step and impulse, and this one would be the speed response for a step input and for a impulse input. How we calculate these things? Well, we can't do it right now because we need to solve the second order differential equations, but we will eventually do that after lecture 6. Okay. Any questions here? No? All right. So let's do a few exercises. Now that's all for what we have to know from this modeling part. And it's not very hard. Right? It's always the same. So let's do a few exercises. Let's start with this one here. We have a tiny microelectrical resonator that is used for in implantable devices for monitoring and treating a cause of heart failure. Pressure changes in the transducer's diaphragm and pressure changes in the transducer will shift to the mass resonance frequency. We can be monitored externally using some sort of sensors. An equivalent model of this sensor is shown in this mass spring damper system. The question is, write the equations of motion for each mass. What you have here is a combination of two masses. It's a resonator, a mechanical resonator, meaning that the input is given at a certain frequency, and you can watch the output. And if the output changes with respect to over time, we can say that some characteristics in that sensor have changed over time. In this case, would be the pressure that the heart exerts on the device. And through that, we'll be able to monitor the condition of the heart. But this boils down to a simple system. It's simply a combination of two masses and a spring and two springs and an input force F of t. We want to calculate, to derive the equations of motion for this mass. So let's do that. You can add the your annotations here. I'm going to solve that in the whiteboard. So here we have the resonator, two masses, two springs, and a force. Okay, so what do we see here? We see one mass connected to a spring that is at a fixed reference frame. These rollers indicate no friction with the ground. There's a mass here and there's a force there. If you want to find the equations of motion, we want to relate displacement or speed or acceleration to the force developed here. So let's give these masses two displacements. So the first one here is x2. That's the displacement of mass 2. And let's give this force, this mass, a displacement x1 of t. That is the displacement of mass 1. And now let's do the free body diagram for each mass. Let's start with mass 2. Which forces are acting on mass 2? Now we need to replace all elements connected to mass 2 by the respective forces they apply. So mass 2 is subjected to the input force F of t. And what else? By the force that this spring exerts on mass m2. So let's think about this. The input is F of t. If you hold mass m1 in place and displace mass m2 along the force, along the input force, which is F of t, to the left, to the right, then this spring is acting against motion, is holding the mass back. Therefore, it must apply a force in this direction. What is the magnitude of that force? Well, the magnitude of the force is the stiffness constant K times the relative displacement of each end of that spring. So it is now the relative displacement is the displacement on this side minus that side, or the other way, depending on how the system is. So we can write x2 minus x1. And you may ask, why not x1 minus x2? Well, that works as well. That works as well. But in case we do x1 minus x2, we may end up with a negative sign. And if that occurs, it simply means that the arrow should be pointing in the opposite direction. The arrow gives the direction, the magnitude is giving here. Magnitude is always positive. If the magnitude is negative, the arrow should be pointing in the other direction. An easy way to, or I would say intuitive way to do this, which is not totally accurate, but it helps, is to assume that, for example, here, F of t moves the mass to the right. So in the beginning of motion, when we start moving, we can say that a mass m2 will move more than mass m1, which is not necessarily accurate, but we can intuitively say that the mass m2, because forces applied to it, it will move first. They will take some displacement for mass m1 to start moving before it settles. So we could say that x2 is greater than x1. So in order to give a positive number here, we need x2 minus x1. If you write x1 minus x2, this would result in a negative value, and then the arrow would have to be flipped. Okay. Those are all forces acting on mass m2. Let's do mass m1. What is acting on mass m1? What is acting on mass m1? Well, if this spring is holding mass m2, is making mass m1 accelerate. because when you we pull on F of t, mass M2 goes to the left. It's attached to mass M1 and will also make mass M1 go to the left. So this force from this spring is exactly the same acting here, same magnitude, but opposite direction. So that when you connect these things together, they will cancel out. Let me just for clarity, let me write this on the other side of mass M1. There is no ambiguity, no confusion with this spring. So this is K, this is K2, right? This is K2, this is also K2. What else is acting on mass M1? Well, we have this spring, and this spring is attached to a fixed reference frame. So that end doesn't move. Mass M1 is moving to the right, what is this? To the right. This is the right, yeah. It is moving to the right. So if it moves to the right, this force will be preventing the mass from moving and therefore applying a force to the left. And the magnitude of this force is K1 times the displacement of that spring, which in this case is simply x1 of t, which is the displacement of mass m1. I'm going to add the displacements here, even though they don't go on a free body diagram. Here they are. Okay. Now notice that when you take this mass and connect it back to mass m2, this force and that force have exactly the same magnitude but opposite signs, so they cancel out. Right. So the force applied on one end of this mass must be the same applied to the other end of the mass, the other mass. All right. So these are the free body diagrams. Are there any questions about these free body diagrams? No? All right. So if there are no questions, now let's do the equations of motion for each mass. Let's start with mass m1. We know that the sum of all forces acting on mass m1 is equal to the mass itself times the acceleration of mass m1. If you're dealing with displacement, this is m1 times x1 double dot, where the double dot indicates second derivative with respect to time. Right, so d squared x dt equals to x double dot. What are these forces? Well, now we need to also create a convention here. If you want to add all these forces, we need to establish a direction in which forces are positive or negative. Because both masses are moving to the right, we can, by convention, say that everything pointing to the right is positive. For mass m1, we have this force being positive, so k2 x2 minus x1 is positive. This force is in the opposite direction, it's therefore negative, k1 x1, and this is equal to mass 1 times its acceleration, x1 double dot. Okay. Let's do mass m2. Sum of all forces equals to m2 x2 double dot. What forces are acting on it? Well, we have two forces. F of t points in the positive direction, so that's F of t. And there's a second force here due to the spring is pointing in the opposite direction, minus k2 x2 minus x1, and this is equal m2 x2 double dot. Okay, and these are the equations of motion for these two masses. Any questions? Any questions? No? What happened if we added a damper? Let's add a damper to this, make it a bit more complicated. Let's add a damper between these two masses here. Damper B. What would change? What would change? Let's start with mass M2. What would happen to mass M2? Well, the damper would. Yeah, go ahead.
M2 would have a force pulling it backwards.
Exactly. M2
And
would
then
have a
M1
force.
would have a force pulling it forward.
Very good. So M2 would have a force pulling backwards. And why backwards? Because if you hold mass M1 and make M2 move, the damper will hold that back. And the force exerted by the damper here would be its viscous friction coefficient times the relative speed between each side of the damper. So x2 dot, the speed of this mass, minus x1 dot, the speed of the other mass. Why x2 minus x1? Well, we can apply the same observations we did here in terms of speed. So if mass m1 now the damper points to the right, to the left, then it needs to point to the right for mass m1. So this is b x2 dot minus x1. Now in this case, look, m2 is the damper is actually accelerating the mass. The damper is accelerating the mass because mass m2 is moving to the right. The damper is creating a force and is dragging m1. So this is actually accelerating the mass. Whereas if we had something like this, for example, and there was damper between the friction between these two surfaces, it would always be slowing down the mass. Right? But it's the same friction, same type of friction. But here it's between an element that exists between these two. Okay, so by adding that, of course, we need to include these forces into the calculations here. So for mass m1, it would be a negative force, so negative b x2 dot minus x1 dot. And for mass, did I do it backwards? Yeah, so for mass, this is mass m1 is positive, so this is positive. And for mass m2, this is negative, so minus b x2 dot minus x1 dot. In case we had this damper there. All right. So this analysis that we did here was with respect to displacement, but we didn't have to use displacement. That's what we chose to use. But instead, we could have used the speed. How would these equations look like if we had used the speed instead? So let me call this speed here v1, and let me call this speed here v2. Let's take this equation here, for example. Would we be able to rewrite this equation in terms of speed? Well, f of t doesn't change. Here we have the spring that multiplies the displacement. But if you want to write that in terms of speed, all we have to do is to integrate the speed, v1, v2 dt minus integral of v1 dt. Now this is the same as x2 minus x1. It's just the integral of speed instead of the position itself. Minus b times, this is x2 dot x1 dot. These are the speeds of m1 and m2. So you could write v2 minus v1. And this is equal to mass times acceleration, so m2. The acceleration is the second derivative of position or the first derivative of speed, v2 dot. Okay. Same equations. With this equation, the variable of interest is the position. This here it's the speed. And it could do the same for acceleration. If we wanted, we'd have to integrate this twice, and then have to integrate the acceleration once, and this would be equals to m2 times acceleration. Okay, any questions? Any questions? No? All right. So there are no questions. Let's do another one. Should we do something much more complicated or about the same level?
More complicated.
More complicated? Yeah, okay. So let's do exercise number 5. I'm going to put it on here. Wow, it is not much more complicated. It's slightly, there's just more stuff in there to model. We have two masses, M1 and M2. What is happening? Mass M2, excuse me, the wire got caught, my shoes. M1 is connected to a spring and damper to a fixed reference frame. There is no friction between M1 and the floor. There is friction between M2 and the surface here. This is spring, that spring, and this is the input to the system. It's a displacement to that end of the spring. So let's give these variables some names here. This mass is some displacement. M1, let's assume that has displacement x1. In M2, am I doing this up? Well, yeah, so this is M2, excuse me, this displacement x2. And this is M1, which has displacement x1. We can now do the free body diagram for each of these masses and replace the effect of these forces, these elements, as the force they produce. So let's start with M2. This is M2. And which forces we have here? Well, we cannot create a free body diagram for this spring because it's not a mass. It has an input, which is a displacement x. This displacement x creates a force because it's stretching the spring, and the spring will make the mass move to the right. So the first force we have here is the force due to spring K3, and the magnitude of that force is K3 times the displacement of that spring. Now, should we write x minus x2 or x2 minus x?
Could you repeat that again, sir?
Should we write K3 times x minus x2 or K3 times x2 minus x?
I would do x minus x2.
Why would you do that?
Because x is really the only one moving. X2 is, if you hold M2 and you stretch x like the K3, x is the only one displacing.
Yeah, we can say it that way, or we can think about this way too. We first need to create a displacement here to see a displacement there. We first need to observe a displacement here to see a displacement there. So we can say that x is greater than x2, which is greater than x1. So in order to get a positive value inside here, we need to write x minus x2. Okay, what else we have acting on mass 2? We have this spring, and this spring is holding the mass back. If you hold M1 and stretch the spring and make mass M2 move to the right, this spring is kind of pushing it back. So it has a force that goes in the opposite direction. And this force has a magnitude of the stiffness. It corresponds to a stiffness K2 times the relative displacement of that spring. And as per our convention here, we know that x2 is greater than x1. So x2, the displacement of this side of the spring, minus x1, the displacement of that side of the spring. What else is happening? Well, there's friction here. Friction in this case is always opposing motion. So if the mass moves to the right, friction goes to the left in this case. And what is the magnitude of that friction coefficient, friction force?
I believe it would be B2 times X2 dot.
X2 dot, exactly. If this is called, it's called B2, let's give it a name, it's called B2. Yeah, exactly. It does not depend on X1 dot, see, because it only depends on this mass and the surface. It's not connected to M1. M1 has nothing to do with the amount of friction this produces. This friction only depends on how fast this mass moves. Therefore, X2 dot, which is the speed of this mass, times the coefficient of viscous friction. Right? So these are all the forces on that mass. Now let's do M1. What is happening at M1? Well, if this spring is holding mass 1 back, this spring there, it is actually making M1 accelerate to the right. All right? If we move X1 to the right, X2 goes to the right, the spring is stretched to the right, and will make M1 go to the right. So this force obviously needs to go to the right. The force due to this spring is K2 X2 minus X1. Now notice once again that this force is the same as that, is exactly the same in magnitude, but it has opposite direction. Actually, I should have written it this. Actually, let me put it here just to avoid confusion again. It's the same force. I don't want you to mix that up with the other one over there. All right, there it is. So that's the first force on mass M1. What else is acting on mass M1? We have this spring and that damper. The spring is holding the mass back, is pushing the mass, is preventing motion. So that spring applies a force K1 times the displacement of the spring. Now notice that one end here is connected to a fixed reference. So it only depends on the absolute displacement of mass 1. That's K1, X1. And the viscous friction here, due to that damper, will act in the same way as if we had friction there. Because the one end is connected to a fixed reference, the magnitude is B times the speed of this mass, which is X1 dot. Okay. Now we have all forces acting on all masses. We can do the equations of motions. Let's start with mass 2. We have the sum of all forces on mass 2 is equal to the mass itself times its acceleration. So if you're talking about in terms of speed, if you're talking in terms of position, that is the second derivative of position. Position of mass 2 is x dot, is x2. So x2 double dot is its acceleration, second derivative with respect to time. Sum of all forces, well, we need a convention again, but because we know that this thing is accelerating to the right, let's assume that everything that goes to the right is positive. We have K3 x minus x2 minus K2 x2 minus x1 minus B2 x2 dot. These are all the forces equals to M2 x2 double dot. Now let's do M1. Sum of forces acting on M1 equals to M1 x1 double dot. Positive to the right, positive, negative, negative. K2 x2, x2 minus x1 minus bx1 dot minus k1 x1, and this is equal to m1 x1 double dot. Okay. Any questions? This is relatively simple, isn't it? No questions? Can we move on? Yeah.
Yes, I believe we're all good.
Okay. Yeah, just as a reminder, I can't see the chat because the monitor is too far away from me. I can only use the monitor to see where I'm pointing, but I cannot see the chat. So if you have any questions, just open your microphone and ask. All right, so if this is all good, let's do exercise 6. This comes from a midterm examination. This is slightly more complex. I'm gonna erase the whiteboard here as fast as I can, and I'll let you read and get started with this problem. This problem here, we only have one mass that sits inside of a casing. This casing is given an acceleration v, and we want to, and the mass inside of that case is given a displacement x. We want to model the system. This is a good example of an accelerometer, a sensor to measure acceleration. If you have a mass inside there with a spring like that, and you know that if you accelerate the casing that holds everything in place, that holds the mass inside will move. And the mass inside will move so long it is subjected to a acceleration. So by measuring how much the mass moves inside of the casing, we can infer the acceleration of the casing itself. Okay, so the first step is always to create a free body diagram. We are interested in this mass in the center there. Let's write it here. Notice that the casing that was not given a mass. Why is that? Because it is already subjected to a speed. So if you want the position, just integrate the speed. If you want the acceleration, just derive the speed. If this was a force applied to this casing, then we would indeed have to consider the mass of that casing and create its own equation of motion. But here we already have its output, we already have its speed. There's no need to account for the mass of it. So all we need to deal with is the mass in the center. It has a mass m. And now what is happening here? The mass sits inside of this casing. There is friction here. Therefore, there is friction. We can assume that there is friction there as well. It's not specified, but let's assume there is friction there. It doesn't matter. There's friction on both sides of this casing, and there is this spring. Which forces are acting on this case? Let's assume on this mass. If you hold the mass and you apply a displacement to the casing here, the casing is moving to the right. The spring will stretch and then also make the mass move to the right. So the first force that is acting on this mass is the force due to the spring, and the force due to the spring depends on the displacement of this side of the spring and the displacement of that side of the spring. What is the displacement on this side of the spring here? Is a displacement of the casing. But in the casing, we don't have here the displacement, we have the speed. So in order to get to displacement, we would have to integrate the speed of the casing. So K times integral of V, that's the displacement on this point, minus the displacement of that point. And the displacement of this point is the displacement of the mass itself, which is given as x. So V integral of V dt minus x. Why is this V minus x, integral of V minus x, not x minus integral of V? Because we can assume that we first need to see motion on this side in order to see motion on that side. We first need to stretch the spring here to see a displacement there. This is not totally accurate, but it's a good way to look at it. What other forces are acting on the system? Are there any other forces? Well, there's friction here and there. Now the big question is, in which way does friction apply a force? Is it going to the right or is it going to the left?
To the left.
To the left. Is it going to the left or is it going to the right? Let me bring back the example of, I have a paper here.
It'd be going to the right. Yeah, it'd be going to the right. Yeah.
It's going to the right. So let me have a paper here and I'm putting the marker on top of it, which is the same that is happening there. The paper is the casing, the marker is the mass. And if I move this to the right, the marker is also moving to the right. And why is the marker moving to the right? Because there is friction between the two, and friction is also making the marker move that way. Of course, this is static friction, so if we are dealing with viscous friction, it would be moving faster, right? But as you move fast, you see that the marker is still moving to the right and is due to friction. So friction is in fact making that move to the right. So this is the friction from the bottom, this is friction from the top. And what is the magnitude of that frictional force? Well, is the coefficient of viscous friction times the relative speed, now speed of the casing and the mass. So one side here is the speed of the casing, which is V itself. And what is the speed of the mass? Is x dot. Speed of the casing, V, already given, speed of the mass as a function of position is this derivative of position x dot. So this is one force for the bottom, and then you have one here for the top. And these are all forces acting in the system. We can now do the sum of forces equals to, equals to, we're dealing with the mass. Mass has position as the variable of interest, so m times x double dot. Sum of forces, everything that goes to the right here is positive because it's accelerating the mass that way. So k times the integral of v dt minus x minus 2 times b v minus x dot, right? So just adding these two up, this two, hence number 2 here, equals to mx dot, double dot, excuse me, double dot. Okay, how we solve this? Now we have an integral, we have a derivative, and have the variable itself as a mass. So we need to take the Laplace transform. We're going to see Laplace transform in lecture 4.
Excuse me.
I got a question.
Yeah.
Does the arrow of the fraction should be the opposite? Not
Should be positive.
should be positive?
Yeah.
All right. Why it's positive?
The effect of friction.
Yeah.
Yeah. So the effect of friction is making the. Let me go back to my example here. This is the casing. This is the mass. Put them on top. If I move the case to the left, to the right, so does the marker, and is doing so because friction between the paper and the marker is making it move that way.
Oh, okay, makes sense.
Right. So hence it points to the positive direction, and this is positive there as well.
Okay, gotcha. Thank you.